So we're working this example. We're trying to integrate 2 times the quantity 2x plus 4 to the raised to the 5th power. Okay, so we could find the antiderivative by multiplying this all out, and we would get a polynomial in x, a degree 5 polynomial. And we know how to integrate things that look like that. We just break it up into different pieces and integrate each piece using the power rule and the constant multiple rule. But we're going to do something different here, which is going to give us a nicer answer. Nicer, but algebraically the same answer as the one we would have gotten by multiplying everything out. Okay, so the idea here is the answer, you want to say that the answer is going to look like 2x plus 4 to some power. Okay, so what we do, so I'm going to write this a slightly different way. We have 2x plus 4 raised to the 5th power times, I'm going to rewrite 2 in the following way. 2 is going to be the derivative of 2x plus 4. And it's a strange, maybe it makes no sense why I chose to do that, but in fact, the 2 is the same as the derivative of 2x plus 4. Okay. So, well, okay. Now, the general power rule tells us that if we're differentiating, say, 2x plus 4 raised to some power, what we do is we bring down the exponent, keep the inside the same, reduce the exponent by 1, and then we have to multiply by the derivative of the inside. And here we have a very similar structure. We have this thing raised to the 5th power times the derivative of the inside. And that's generally what the sort of problem that will work well with integration by substitution. Okay? And in fact, you could guess, if you wanted to, that the answer should be something times 2x plus 4 raised to the 6th power. And then we'll actually need a 1/6 out front, because we're integrating. And then we'll have a constant of integration. And let's check that we did this correctly. So if we differentiate 1/6 times 2x plus 4 raised to the 6th power plus c, then we'll get 1/6 times the 6, which comes down from the exponent, times 2x plus 4 raised to the 5th, times the derivative of the inside, 2x plus 4. And the 1/6 and the 6 cancel. The 2x plus 4 raised to the 5th stays the same, and the derivative of 2x plus 4 is going to be 2. So in fact, we do end up with the integral as the derivative of our answer, which is what we want. So this will be the antiderivative of this. And what we're going to do, instead of sort of this leap, what we're going to do is we're going to pick a new variable. I'm going to use u all the time for some reason. And we're going to let u encapsulate a lot of the complexity of the problem. We're going to sort of stuff the complicated part into u. And then, so in this case, the problem looks like basically 2x plus 4 raised to some power. And I would really prefer to do the integral of a variable raised to an exponent. So what I'm going to do is I'm going to literally just replace this base with a different variable, u, and then I will change this integral to an integral in terms of u. So if u is 2x plus 4, then when we learn differentials, we know the relationship between du and dx. And the relationship is that du is going to be 2, which is the derivative of 2x plus 4 with respect to x, times dx. Okay. So now, so the integral that we're trying to solve I'm going to replace the 2x plus 4 by u. Actually, let me write this slightly different. So we have the 2x plus 4 raised to the 5th, and then we have a 2 dx. And basically we will replace the 2x plus 4 by u, and the 2x dx, I'm sorry, the 2 dx with du. So that the integral looks like the integral of u to the 5th du. Now, this integral, the integral of u to the 5th, is much easier than the integral we started with. And that is the idea. We've replaced x with u, we've simplified the integral, and now it's easy to find the antiderivative of this, just using the power rule. So we integrate with respect to u, and we have to increase the exponent by 1, and we also have to multiply by a constant. We have to divide by the new exponent, so that when we differentiate this, we pull down the exponent, the coefficient becomes 1, and then we have u to the 5th, because we have to reduce the exponent by 1, and then we have the constant of integration. Okay, so that is an answer. That is an answer to this integral, the integral of u to the 5th, with respect to u. But that's not what we want. We really want to solve this problem, which is an integral of a function of x with respect to x. So our answer should really be a function of x. So we changed from x's to u's, made the problem easier, solved the integral there, and now we're going to actually change from u's back to x's so that we get an answer to our original problem. So what is u in terms of x? U is just 2x plus 4. So we just replace u with 2x plus 4. And now we get 1/6 times 2x plus 4 raised to the 6th power plus c as our answer, which is the same answer that we got sort of guessing from this step to this step. So hopefully that will give you some idea of, or will help you to believe that this process works, this process of u substitution. So, I want to summarize the steps we did in solving this problem. So use substitution for this integration by substitution method will work for a particular kind of integral. And it's going to work for an integral which has this general form. We're integrating f of g of x times g prime of x. So you want to look at your problem and try to put it in this general form. You want to somehow make it look like this. So the key step in doing this example was seeing that there is an operation of raising something to the fifth power, and that's going to be what f is. And whatever we're raising to the fifth power is going to be g, and whatever else we have, whatever else we're trying to integrate, turns out to be exactly just the derivative of the inside. And so that's how this example fits into this sort of scheme. This is the pattern you want to look for in the problems that you're trying to do, in the integrals that you're trying to do. I have to admit, sometimes it's hard to make problems look like this, or to see how they fit this pattern. Okay, so we want, for integrals that look like this, what we're going to do first, we're going to pick a new variable, say u, and we're going to let u be g, that function. Or this is how you, this is the function which, or the equation which relates u to x. Okay, so u is given as a function of x, and here, remember, g is going to be the inside of the composite function that you're trying to integrate, where you have functions composed with each other, like in this case where you have a function or an expression, and then you are taking the output of that and raising it to the fifth power. So you have to figure out how your integral is of this general form. Then we pick a new variable u, use the inside here, inside expression, to write u as a function of x. And then, to fully replace all the x's and dx's with u's and du's, we need to figure out what du is in terms of x and dx. And du, the differential du, is going to be g prime of x dx. So basically we just have to differentiate this, this function g.